Hello YouTube, this is my first video over the concept of what we refer to as expected value in probability. Okay, we're going to start by introducing what we mean by expected value, but a lot of time when we look at things such as game theory or games or maybe how much we pay out for insurance claims and how likely we are to have to pay for each insurance claim or medical data. Basically, what we'd like to know is what is the average gain or loss if you were to run all possible variations of that sample space. So we kind of look at expected value as a concept that describes a long-term average for that experiment. So we're going to go ahead and start by formally defining this and kind of exploring it by a couple of thought experiments here. In my next video, we'll talk about how to make a game, say a fair game, using these same concepts. But we say the expected value of a discrete random variable of a probability distribution is the theoretical average of the variable. And so the interesting thing about it is this. I've already, of course, made a couple of videos over finding the average of a discrete probability distribution. But the expected value, we define it as being this function e of x. But basically it is defined as the same thing as the mean. So expected value, when you see expected value, we can just refer to it as this. It is the mean. So the good news is this. If you're tuning into this video and you're already cool with how to find the mean of a discrete probability distribution, then you already know how to find expected value. It's just now we're going to interpret it a little bit differently, okay? So we loosely define this as the sum of all of the data points that could happen times the likelihood that they do actually happen, okay? So this really is the definition of the mean. And just to reiterate the fact, we use e of x to represent the expected value. You can think of e as being expected value. But let's take a look at what it is that we mean by expected value. So let's consider this first thought experiment down here. It says 1,000 tickets are sold. We'll sell them at $1 a piece, okay, for a colored television valued at $350. We want to find the expected value of the gain if a person purchases one ticket. So now I want you to, before we kind of go through this, consider this. What if you were running this game? Would you be happy running this game? Do you think you would come out on top? And the bottom line is this: if you sold all 1,000 tickets at $1 a piece, hey, you'd be making $1,000. You would make $1,000. And if you were losing the television, that is, you had to give the winner the television here, that would mean that you're necessarily out like $350 essentially. But basically what I want you to realize is this: you made $1,000, you lost $350. What it comes down to is this: you made $650. This is what you made. So this would be a great game if you were the person running the raffle, because of course you would have a net gain of $650 total. But what we're trying to assess here is this: so what was your average gain per ticket? So that is, if you were to play each individual ticket, how much did you win per ticket? Now, of course, we didn't actually get the entire dollar per ticket, and the reason why is because we had to give up a TV. So if I wanted to find out, well, how much did I gain on average per ticket, we're taking the trivial approach here first. We're saying, well, we made $650 total, and we had 1,000 tickets. Okay, so if you wanted to look at it this way, how much did you make per one ticket? And we could scale this down, of course. We could say, well, 1,000 down to 1, this is divide by 1,000. We still haven't even started the probability approach to this yet, but we basically say this: on average, per ticket, we made 65 cents. And if you think about that, it's entirely reasonable, because if we had a net difference or a net gain of $650, then we must have made on average about 65 cents per ticket. So when we approach expected value, this is what we're trying to determine right here. On average, how much can we expect to gain or lose? And in this case, we got a positive number, which means we must have been gaining money per ticket. So now how would I do this as a probability experiment? Well, you notice here I write, start by constructing a probability distribution for the amount of gain x. So the first thing I want to acknowledge is this: we're going to allow our discrete random variable x to represent the amount of gain that you get in this experiment. So when we make our probability distribution, of course, it's a row by column array, but we're going to say x, and this is representing the gain, and we're talking about in dollars, okay? And then the likelihood that I do actually gain this. So we're going to start up with the gain. Now, what we're going to put up here is all the possible situations that would exist. And so I guess what I'm saying is this: in this experiment, what is your potential for a gain, okay? So let's look at this from not the running the experiment or running the raffle point of view, but as a player. I mean, if you were to play this game, of course, you would be at a disadvantage. You are likely to lose, but on average, how much would you be expected to win or lose per ticket? So we say, well, what are the possibilities? I mean, what could happen when I run this experiment in terms of spending money? Well, I know one thing that could happen is I could spend $1 and I could lose that dollar. So one thing we're going to want to put up here is this, in dollars, I'll put $1 here, is we could lose $1. You know, we could lose that dollar that we had bet. Or the thing is, we could win the television. I mean, like, we could either lose $1, we could win the television. And if we win the television, our gain would be $350. Now, there are actually videos that you're going to find on YouTube, and there's nothing wrong with these videos. There's different intuitive approaches to these things. But you might be thinking to yourself, well, actually, you didn't gain $350 because you actually bet $1 and you never got that dollar back. So technically, you only gained $349. But we're going to kind of take a different tact at approaching this one here. And it's a little bit easier to deal with, okay? So we say, well, I think these are the only two possibilities. I could either lose my dollar or I could win the television that is worth, you know, in terms of value, $350. So now what we want to do is we want to calculate the probabilities for these. Well, I personally think it's helpful to, when you talk about probabilities, to draw out the sample space to see what you're dealing with here. So when we talk about winning or losing, you know, of course we would have like lose, here lose, or we would have win. We could split our sample space up into these categories where we're talking about the tickets. So in terms of a winning ticket, we have one winning ticket in the entire batch. Now, how many tickets were there total? If we read this problem correctly, there were 1,000 tickets that were sold. Okay, so we say, well, the sample space size is 1,000. So if there's one winning ticket, in terms of losing ticket, you know, we have 999 losing tickets. But this is our sample space here. Okay, and now looking at this, we can use this kind of diagram here to go back and assess the probabilities for each, you know, possible thing that could happen. So here's the interesting thing about this. We say lose $1. The real question is this, how many of these 1,000 tickets are you going to lose your dollar for? And the thing that I'm going to do a little bit different than you'll see in a lot of other videos is this, the thing is, you always lose your dollar. I mean, you're never going to get this dollar back regardless of whether you win this television or not. So what we're going to put down here is this, for how many of the 1,000 tickets do you lose your dollar? We're going to say, well, for all 1,000 of them. For 1,000 1,000ths of the ticket, we are going to lose this dollar. And we know this is intuitively obvious by looking at the picture over here, but we say, okay, so now how about winning? I mean, winning this television, what percentage of the time could we expect to win the television, or what is the likelihood we win the television? Well, it's 1 in 1,000. The reason why is because out of the 1,000 tickets, there's only one winner. Okay, so going back to the fact that when we talk about the expected value or the expected quote-unquote gain for this experiment, we're talking about the average or the mean, okay, the population mean here. So what we're going to do is this, we're going to drop this down here. We're going to add in a third row. This is just like finding the average. So we say x times the probability of x. We're going to take everything that can happen in terms of gain times the likelihood that it actually does occur. So for instance, if I take -1 times 1,000 1,000ths, what I turn out is this, I get -1,000 out of 1,000. And if I were to take now this x value up here, 350 times its probability of happening, we get 350 times 1 1,000th. Well, 350 times 1 is 350, so we get 350 1,000ths, okay? So it kind of looks like this. We say, all right, well, what we wanted to do is we wanted to sum. We wanted to sum all of these, which means add them together. I'm just going to write a sigma over here. I'm not going to write the whole formula, but the sum of these, we would say, well, out of 1,000, if you were to add -1,000 to positive 350, you'd turn out -650 over here. And of course, we are talking about dollars. And so I am going to simplify this down into a decimal because, you know, with dollars, we usually talk about dollars and cents. But we say, in terms of what we just discovered here, we got negative dollar amount here, 650 thousandths, which, you know, if I wrote that out, it'd be 650 thousandths like this. But I'm going to write it as, you know, reduced. We could knock off, of course, a 0 on top and bottom. Negative 65 hundredths. Okay, so we're going to give this a name. This is E of x, and this is also mu, and this is also the expected value. Okay, and what this is, you know, if we want to write this down here, is a long-term average. And essentially what it's telling the audience member is this: if you were to play one ticket, then you will have lost on average only 65 cents. And the reason why is because you have a potential to gain the television. So you didn't lose your whole dollar, okay, because you had the potential to gain the TV. But I also want you to think about it this way. What if you were the sucker that spent $1,000? Actually, I don't want to say a sucker, because maybe it's going to a good cause, right? But what if you were to spend $1,000 and buy every single ticket that there was? What this means is, in terms of what you spent, you spent 1,000. That's negative 1,000. But what you gained was 350. And when you glue these together, you get negative 650. But thinking about it, you played 1,000 tickets. So you lost negative $650 on all of the tickets, on everything that could have happened. But per ticket, you lost 65 cents per ticket. And I get it. You can't lose 65 cents a ticket. But what we're saying is on average, you're losing 65 cents a ticket. Okay, so that is what we mean by expected value. So let's take a look at one more example before we close this video out here. We say 1,000 tickets are sold. This looks familiar, at $1 a piece. But let's put it this way. We have 4 prizes in this instance. We have $100, $50, $25, and $10, okay? So we say, what is the expected value per ticket if a person purchases 2 tickets? And in this instance, we're going to let the discrete random variable represent the amount of gain that is in dollars, okay? So when we consider it this time, we have a little bit different of a sample space necessarily, okay? So what we're going to look at it is this way. We say, all right, well, let's start by defining X. We say X is gain in dollars, gain in dollars. Okay, so when we look at our probability distribution here, let's go ahead and set up our rows here. We say X, and then the likelihood that X actually occurs, okay? So we say in this experiment, well, what are all the things that could happen here? And keep in mind that we're purchasing 2 tickets in this instance, but we say, all right, well, I suppose I could win $100, win $100, or I could win $50, right? I could win $25, put my dollar symbol in here. I could win $10, or, now keep in mind, we purchased 2 tickets. Okay, so we could say I would lose $1 per ticket. Actually, we say just $1 per ticket. We say, all right, I lost $1. You're going to lose $1 per ticket. We'll do the 2 tickets here. I guess we don't have to consider the 2 tickets. If we were to purchase a ticket, how much do we gain or lose per ticket? So these are all the possibilities. I could win 100. I could win 50. I could win 25. I could win 10, or I could lose $1 per ticket. And we say, well, what are the probabilities of this? Again, I think it is very, very useful to draw out a sample space here. So we could say, win $100. I suppose there was 1 ticket that would do that for you. We could win $50. There was 1 ticket that does that for us. We say we could win $25, which there's 1 ticket that does this. We could win $10, which is 1 ticket that does that, and then all other tickets, in our entire sample space here, of which there were 1,000 tickets. So if we've got 4 tickets that would win, then we say we got 996 other tickets that would lose, okay? But, this is going to help us determine our probabilities. So again, let's determine the probabilities. We say, well, how likely is it that I win this $100? Well, there's only one thing that wins me this $100 out of 1,000. So this is a 1 in 1,000 chance. And likewise, it is 1 in 1,000 chance for all of these other prizes because there are only 1 of each out of the total of 1,000. Now, here's where we come back to the sticking point. Again, with probability distributions, usually you'll have all of your probabilities add up to be a total of 100% of the stuff. And, that's good to have. But with expected value, sometimes it's easier to just take the approach of, well, when do you lose your dollar? Well, you're going to lose your dollar all of the time. So like 1,000, 1,000th of the time. For all 1,000 tickets, you're going to lose your dollar. So now let's go ahead and make an amendment to our tableau here. We say, all right, we'll drop these down. We'll go ahead and find our long-term average. So we say, well, this would be 100 out of 1,000. This would be 50 times 1 1,000th is 50 1,000ths. Of course, 25 times 1 1,000th is 25 1,000ths, and 10 times 1 1,000th is 10 1,000ths. And we say, all right, negative 1 times 1,000 1,000ths is negative 1,000 1,000ths. And so if we actually do indeed take the sum of all of these, of course, I'm going to write it down here, we get 1,000ths. We say 100 plus 50 is 150, plus another 25 is 175. Now 175 plus 10, that would be 185. Now if you added 185 plus a negative 1,000, I believe we get negative 815 here. Okay, and again, we're measuring this in dollars. So one thing I want to be clear on is this: we should probably put this back as a decimal. So what this means is negative 0.815. Okay, and again, we're going to give this a name. This is our expected value, expected gain. But what this means is we are expected to lose. Lose. You wouldn't want to play this game unless, I guess, you were going for a good cause again. Per ticket. Okay, so when we talk about expected value, it is just a measure, an assessment of the average win or loss per ticket. Okay, so as a preface to my next video, I'm going to go ahead and beg the question: what would you want your expected gain or loss to be if this game were completely fair? That is, you were to neither lose money nor win money per ticket. On average, how much would you expect to gain if you neither lose nor you win? Cheers.